Okay, so last week we kind of talked about the toy example of an artificial neural network where we had two inputs, three hidden this is our input layer, our hidden layer, and then our output layer. Okay, and then we scaled all of the data so everything's between 0 and 1, okay, between 0 and 1, and then this was also an output between 0 and 1, and this was like, and so we had 9 weights, and and we adjusted them. We applied gradient descent, used gradient descent to train our network. Okay. Okay, and essentially all gradient descent is you calculate. So you find the you have your cost function. Depends on the weights. Okay, and what we did is we applied gradient descent. We calculated the gradient at our current weight locations. Okay, so gradient descent is find the gradient at the current location, of W. Okay, and then you subtract some lambda times the W from lambda times the gradient from W. Okay, and then repeat. And you just do this over and over, taking steps in the direction of the gradient. Okay. Yeah, that's what the for loop is. Okay. And the hardest part is calculating the gradient. Okay. So the hardest part is probably doing the calculus to find the gradient. So, or actually, well, that's my opinion. Okay. All right. Well, we can advance this, make things a little bit more complicated. Okay. I'm going to just make our model just a tiny bit more complicated. And so what we will do is so remember what kind of the steps to go from the input data to our predictions is first we take our input data X, and then we multiply it by our first weight matrix. Okay, and this one we called Z. So those are here are the X's. We multiply it by W, and that goes into Z. Okay. Then what do we do to Z? We apply a sigmoid function to Z. To get A. Okay, and so that's kind of the output of our nodes. And then we multiply A by our weights, by our second set of weights, to get kind of our, I guess the notation is to get our, our Z's for the third layer, okay? And then we apply the sigmoids to the Z's here. Okay. All right, so what we're going to do now, and here our outputs were on a scale from 0 to 1, kind of indicating like a percentage on the test that we were looking at. Okay. Let's see. This is. So we're gonna make our model a little bit more complicated, and I was debating how much. Well, I don't know. I'd like to make an assignment out of this, but I don't know if I can. So, because it might put a significant amount of coding burden on you guys, but I think you guys could handle it. So, but we'll see. And I think you'll have a good sense of accomplishment when you pull it off. All right, so we're gonna make our model a little bit more complicated for this example of handwriting recognition. Okay. Okay, and so we're going to use what's called the Amnesty Data Set. Okay, this is kind of a famous machine learning data set. Okay, or Amnesty database of handwritten digits. I'll post this up. Okay, and you'll download these files. Okay, and these are like binary files. They're not recognizable as digits. Okay, it's just it's a mess. Okay. Luckily, this is kind of a well-known data set or database, and so people have written a lot of code already for it. A lot of the code is written in Python, and if this were a different class, we would probably be using Python. But here we're gonna use R, and R is still very capable, and I think a great use or great resource for this, and we'll do it. And so there on CCLE, I've posted a link to kind of the code that we will use to take this data and put it into a format that R can understand. Okay. And so what you'll do is you're gonna download those files. Okay, and you're going to need some kind of unzipping tool. So if you're on a PC, I use 7-zip. If you're on Mac, I think your Mac can, because it's Unix-based, can unzip these GZ files quite easily. So anyway, you're going to download all 4 of these. You're going to unzip them, okay? And put them in some directory that you can work with. And I have the link posted to this bit of code, which basically takes it from binary data and makes it into something that we can understand as in R. Okay, so it reads the binary data, which we won't really recognize, and then it creates train and test, which are basically 2 lists. Okay, it's going to load train as a list and test as a list, and then we can take a look at, and then it creates a function to actually display the digit. Okay, and each of these digits, it's a square. It's a little just for the simplicity of everything. It's a 28 by 28 pixel image, okay, and it's grayscale. And it goes from 0 to 255, kind of in. So every single pixel, you got little. And then some of these are shaded, so you have. And And then, you're hoping the computer looks at that and recognizes, hey, that's the digit 4, or something like that, okay? But these are scanned from handwritten samples. Okay? And so the way we're going to format it is, 28 by 28 is 784. And so what we're going to have is each row, our matrix, our input matrix, will have 784 columns. Okay. And then we have a total of 60,000 training images. So this is a very big, big thing, okay? And so each row, it has a bunch of little numbers. Most of them are zeros because it's mostly white, and then where you have the writing, probably 255 to indicate black, or if it's kind of at the edge of the thing where it's being scanned, maybe something a little bit lighter or something like that, okay? And so all of these kind of represent all the different pixels. And so you have 784. And then over here, we have our output, which is the actual digit. So maybe this is the digit 4 or something like that. Okay? And so what we want to do is we want to say, hey, can you take this basically 28 by 28 image expressed as a vector of 784 digits and find some way to say, hey, the number represented is the number 4. Okay? So we'll just take a quick look at the data here. So so I've already loaded it into R. It doesn't take very long. This is actually very well written code here, and I've got the link. The one thing is that when I unzipped the file, okay, the path that existed in the code that exists online didn't exactly match the file names and the path that I had, so you might have to just change this just a tiny bit so your file names match. Otherwise, it's going to say file not found, right? Okay. And so if we take a look at let's do a structure of our training data set. Okay, we have it says n, there's 60,000 rows. Okay, x is a 60,000 by 784 matrix, and then y is just a vector of 60,000. Okay, so we can say what's train $x, and we'll just look at that first row. Okay, this first row. So there's oh, okay. So this is just a vector, right? It's just a vector, and let me just show you. So this is 784 numbers, okay? And so if I say, hey, print out train, what's the last thing? Okay, print out that first row, we can see, okay, it's just a whole bunch of numbers, 784 of these things, right? Well, because the image is 28 by 28, if I resize my window so that it kind of displays 28 rows across, it ends up and I ask for the printout, you can almost kind of see the image itself, because where the zeros are, it's almost like it's white there, and then when the numbers are dark, like 253, 255, it looks dark, and so you can kind of almost recognize that, what number is this? It looks kind of like a 5, right? And we can ask, hey, is that a 5? And we can see the label associated with the first output, and it says, yeah, that was a 5, okay? Or we can say, hey, let's look at that second number. Okay, what does that look like? A 0, okay, yeah, this is kind of fun, right? All right, and it says, oh yeah, that was a 0, okay? And there's the when you load this, you get the function show digit, okay? So basically, it's just a graphing operation. So I can just say show underscore digit, okay, which just takes the thing and it creates an image. Okay, so over here, you know, where the line is dark, like 255, it shows up black, and then at these edges, where it's a little bit lighter, we get grayscale. Okay, so we could see, you know, that first image. This is a 5. Okay. That one's a 4. Okay. So on and so forth, right? So we have just these different handwriting samples, and they're all just digits 0 through 9, okay? And we want to train our network to say, take an input of a vector of 784 digits and somehow weight these properly and say, I think the digit is this, okay? All right, so how are we going to do this? Okay, well, this is how we'll set up our network. Okay, is so my input. How many nodes do I have on my input? How many inputs do I have? Each image has how many values associated with it? I got 784 numbers here, okay? So my input layer is going to have 784 nodes that range from 0 to 255. Now I'm going to scale all of these to be between 0 and 1. So when we build our network, we're going to just divide everything by 255. And we're going to, we'll have 784 values going in, and we're going to scale them from 0 to 1, okay, where 1 means it shows up black on the image, and 0 means it shows up white on the image. Okay, and so our network is going to be we're going to have 784 nodes, and I'm going to go on to the next slide. Okay, so our input layer, 784 nodes. Okay. So all we're doing is we're just ramping up. Okay, and then we have a hidden layer, and how many nodes we want in the hidden layer doesn't really matter. Okay, I mean it does, but it's not like. And so, you know, each of these nodes will feed into each of these hidden layers. Okay, so you're gonna have all of this business, and so you're gonna have this really crazy network, right? Same, you know, blah, right, okay. Okay, so you have all of the connections going from the input layer to the hidden layer, okay? All right, and then our output, we have a few choices, okay? So our output, we can say, okay, we're going to go from either 0, 1, we can have one output layer, okay? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? But if you do reading on this, and this is, you know, this is more of a classification problem rather than a regression problem, okay? So a regression problem means your output is kind of on a scale from, you know, an interval of values. But here we've got more of a classification issue. Is this a 0? Is this a 2? Is this a 7? And so what we're going to have is we've got 10 possible digits. So our output layer will have 10 digits, or 10 nodes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and basically, okay, so we have the mess of connections from the hidden layer to the output layer. All of these. Okay, so just imagine this. Okay, so we have 10 nodes, and basically we're gonna one node per category. Okay, and so if the digit is 0, then our outputs will be 1 associated with this one. So this will be our kind of our 0, and this will be our 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this one, the 0 will be a 1, and everything else will be a 0. Okay, so our output with 10 digits will be 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, okay? That's the idea, okay? Or if the digit is a 4, then we'd have something just, or if, if digit is a 4, then our output will be 0, 0, 0. So this is 0, 1, 2, 3. The fourth, the node corresponding to 4 will be a 1, and then everything else will be a 0. Something like that, okay? And so, so this is how, so we're going to re-express our data as such. And so, just requires a little bit of creativity with our functions to change how we're going to do it. And then, so now we have kind of our inputs and our outputs for our training data. All right, and we're going to build up our neural network this way. Yes. Yeah, the output's going to be a vector. Okay. And for the 60,000 images, our output will then be a matrix. Okay, because you're going to have one row for each image. Okay, so you got, so the output, you feed it in 700, you feed it in a 28 by 28 image, okay? We re-express that 28 by 28 image into a vector of 784 values, okay? Those 784 values go in, we multiply them by some weights in our, and we apply the sigmoid function in our hidden layer, okay? Those now values then go to our output layer, where we multiply by weights, and we apply another sigmoid function, and we're hoping that the output of our sigmoid output after that is going to be a vector where everything is zeros except for one value here. Okay. So so this is what we got. Does this seem okay? All right. Okay. And so as I was reading, one of when they applied the sigmoid function, so remember our steps were we take our inputs x, we multiply it by our weights, and we get our z's. Okay. And then when they applied the sigmoid to z, what they often did was they added a kind of a a bias. Okay, so they add a bias to the z before applying the sigmoid. Okay, so what would adding a bias do when we apply a sigmoid? Okay, so keep in mind that our sigmoid function goes from it goes from negative infinity to positive infinity, and it ranges from 0 to 1, okay? And then, at 0, it's at 0.5, okay? And so all this adding a bias does is it just takes your, this thing, this function, and it just slides it, okay? It just slides it along here, whether, slides it a positive amount or a negative amount, okay? So after adding a bias, so this is, this would be actually the negative b, you're basically just sliding the function over. So that, yes? This is just the terminology, okay? You're just adding a constant to this value z, okay? So over here you have your inputs x, and you multiply them by your w's, okay? And then just to kind of give your neural network, even more places for refinement and adjustments, we're going to add just a constant, which we call b, or the bias, and all that does is just shifts where the where it shifts from 0 to 1. Okay? Yes?
Why is not positive b?
So when I drew this, I shifted it to the right, okay? But so if b is a positive value here, okay, adding a positive value effectively shifts it to the left, right? So now, whereas if z were -3, it would be at down here, right? But then if our bias is 3, if b is equal to 3, then effectively, if b equals 3, then effectively I've shifted kind of this inflection point to -3 now. Does that make sense? Because if this is z, this is now z plus b. It's just like if you think back to just your days from like algebra and pre-calculus, if you're talking about like shifting your graph, when you add a constant, it shifts it to the left, right? And when you subtract a constant, it shifts it to the right. What? Like.
If you have +3, you move your say you had an absolute value graph.
So okay. All right. An aside here. All right. So let's say you have a sine of x. All right. It goes like this, right? Okay. And then if I graph sine of x plus 3, what happens to the graph? Do I shift it to the right or do I shift it to the left? I shift it to the left 3, right? That's all we're doing. That's all we're doing. Okay. Okay, so this is what we do. Okay, we get our a, then we we multiply it by our w's again, and we get our other, and then we apply the sigmoid to z plus our other biases. Okay, other set of biases, and then and this is effectively our outputs. Okay. And lots of different people have attacked. If you look up neural network MNIST, you're going to get thousands of hits, and a bunch of people have tried different methods and different things. Okay, so how do we choose a cost function? I'm going to just keep it simple, and we're going to just use the squared error cost function. Okay, but if we want to use a different cost function to evaluate how good or bad of a fit we have, we can do that. Okay, so. More common is just to use the built-in neural net, or like kind of these packages that people have built up on neural networks. We're kind of doing this, for the sake of education and understanding. We're coding all of this stuff by hand. We're coding like, okay, now we're going to do the cost function, not by hand, but just like we're programming each step ourselves. Okay. Yeah. Probably what exists more common out in the field. You type in neural net, X is this and Y is this, and you say go. All right. We'll get to that eventually. Okay. But for now, we're doing it this way. Okay. So so our cost function will be y minus y hat squared, and then we're going to sum this up, and then just for kind of the simplicity of our derivative, we're going to divide it by 2. Okay. Okay, but y is now a vector, right? It's now a vector. But it still applies. Okay, y and y hat, these are now vectors. And so this is what we got. Okay. All right. So when we're gonna have to do some calculus here, and I don't have those with me. But basically, we have to find the gradients. Okay, so use calculus. Gradients with respect to our weights and our biases. Okay, and so if we think about all of the weight matrices that we have the first weight matrix. Okay, and then we have the first set of biases, which are applied in the second layer. Okay, and then we have the next set of weights, which are multiplied by that second layer, and then we have the biases that get applied to the third layer. Okay, so we gotta we have to find the derivatives or the gradients for all of these things. Okay, find all of these. Okay, so once we calculate all of those gradients, then we can apply gradient descent. Okay. Now here's we could go naively and just apply this to the full data set, but this will be very computationally expensive because there's 60,000 rows. Okay. So they have one method to handle all of these rows is called stochastic gradient descent. Okay, so sometimes you'll see, you know, stochastic this and that basically just means now we're mixing in some probability in here, okay? And so instead of taking the entire 60,000 row matrix, okay? Okay, so instead of processing the entire matrix of 60,000 images, or 60,000 rows, with each step, what we're going to do is we're going to just randomly sample a small selection, okay? We'll take a random sample of images. Okay, so we'll take a random sample of images or rows, and then apply gradient descent to that. Or I guess, and use them in our gradient descent step, okay? Okay, so we, you know, so you got kind of the big matrix, 60,000. All right, and then so you're going to just sample. See, now you have a much more manageable matrix, maybe 10 rows, okay? Still 784 columns. Okay, use this to calculate the gradient. Okay, and then you take a step, update the weights, and update W and B. Okay, and then you go back and you select another 10 rows, and then you do that. Yes.
Professor, what's the typical proportion of the sample size against the whole observation? Is there a recommended proportion?
No. I mean, so the thing about the stochastic gradient descent is that, yeah, you don't, it doesn't have to be like, if you want to do 20 rows or 30 rows or whatever, it basically just, it's so you can speed up your computations, okay, in this. And you know, you're depending on how you do it, in our bit, we're gonna kind of just like take a chunk and you know, kind of split this 60,000 into 6,000 chunks of 10, and then we'll just process one of those things at a time. You don't have to do it that way, but that's one way to go about it. And yeah, you just, you know, you take your sample and you take a step. You know, with stochastic gradient descent, it scales up nicely. So, you know, whether we're looking at 60,000 rows or even more or less, you know, by splitting it up into chunks of about 10 or 20 or whatever it might be, our computations remain fast. I mean, it's a big data set, so if you know, but the hope, okay, the idea behind stochastic gradient descent is that we don't have to look at all 60,000 to get kind of an idea of which way is down, okay? That the idea is we can look at a selection of 10 or, you know, maybe more or maybe less to get just a, you know, a sense of which direction is down, and we take a step in that direction, okay? Yeah.
Is there an instance where you might take a sample and one sample goes down and the other one goes up?
It's possible. It's possible. Okay. Yeah, like if by random chance your sample of 10 all had the digit 1 or something like that, okay, then it's going to say, oh, the best way to optimize is, you know, to go this way, and then you take another sample and maybe they're all 8s or something, and it's going to look differently. So, but the idea is, whatever set you're looking at, you're gonna take a step downhill. So I guess yeah. I'm trying to think, like, you know, in kind of like our two-dimensional example, you know, it's like you've got this terrain and you're trying to walk downhill, but with each step, people like cover up part of your eyes, and so you only get kind of a glimpse of what's out there, but you can still kind of get like an idea, like, oh, this way is more likely to be downhill than this way, so I'm going to go in that direction. And maybe you take steps in the wrong direction every now and then, but overall you should be headed downhill, and that's that. Okay. Or like, oh, here, maybe you know, as technology has improved, like you know, when you play video games, like today, you can have a very nice, like, high resolution landscape, and you can see exactly the terrain, and you might be able to pick out the exact direction, which is the steepest slope, because we have all of these, all of this definition defined. But if you were playing back in the days of early 3D computer games, you know, the hills are all super blocky, right? But you still know which way is downhill, okay? Maybe this direction, just because the hill is like so blocky, this seems to be the steepest, and it's not really the steepest. But overall, you're still taking steps in the correct direction, and that's basically all we're doing here. Okay, so so when we implement our algorithm, we're going to apply stochastic gradient descent. We're going to take samples from our image set, so we don't have to deal with the full 60,000 matrix, and then we take a step in what we think is downhill at that time, update our weights and our biases, and repeat. Okay. So again, you know, the most complicated is finding the gradient, calculating the gradient. When you talk about artificial neural networks, that's kind of known as back propagation, which basically just means, you know, when you take the derivative of something, you have to keep applying the chain rule, right? And so it's just saying, okay, well, we want to take the derivative of the outputs y as a function of w and b. So we see, you know, we got to, you know, we get it with respect to you know, this weight matrix. Then we apply the derivative because we got to keep working all the way backwards until we finally get back to our input layer. Okay, I'm going to give you guys some reading to do regarding this, so please do your reading, and we're going to look at this thing. This is all talking about Python, and he talks about just kind of neural networks and all of this stuff. You don't have to do the exercises or anything, but read and just make sure you kind of understand each step as he's talking about them, and then and you can take a look at the Python code. But if you're not familiar with Python, don't sweat it. We're gonna write it in R, and I hope you'll at least understand the R code, and I think we'll make a homework assignment related to some of this stuff. Okay, all right, we'll see you guys in a couple